Good morning, everyone, and welcome to the masterclass. As part of the masterclass, we will be trying to learn all those additional concepts which are required for us to have knowledge on as a data scientist. This is going to help us design the machine learning models or the solutions that we're developing with respect to analytics is going to be more appropriate. And it also allows us to decide on what kind of resources are we going to consume in order to develop that particular solution. So there are multiple aspects, technical aspects, the hardware, the software, right? All these things will come into the picture. And this series of masterclass that we conduct will allow our students, our participants to gain the knowledge on all these add-on concepts. Now, if I talk about the data science world, the analytics project is implemented using the standard methodology called CRISP-MLQ. Right? This is something everybody is familiar with. Now, as part of the CRISP-MLQ, the first step would be understanding of your business and data. So under this stage, right, at this stage, we will try and understand the business requirements. We will try and understand the various conditions, aspects of the business, how it is run, who are getting involved, how they are getting impacted directly and indirectly, what all various points, data points are getting generated, right? Or everything basically, we'll try and understand in and out of the business. And then we define the specific objective that we are going to solve in this particular project, or in that particular project, whatever the project that you're going to work with. And we also record the constraints or conditions. So these are the points that we will have to define with respect to the business side of things, the requirements. Now, as part of business understanding and data understanding, we try to gather as much requirement information as possible. Requirements. Now, when we're speaking about these requirements, we are trying to understand the various, I should say, points on how the business is run and what kind of data it is generating. And along with that, we're also trying to understand what kind of infrastructure the organization is using. This is one of the important points that we will also have to understand. So before we actually collect the data, we analyze these conditions before actually getting your hands-on to the data. This is to ensure that as a project manager, as part of this step, we'll also, right, if you are a project manager, you understand, you'll also have to understand what kind of resources we will have to define for the project. There are certain points that we also have discussed as part of CRISP-MLQ before data collection. We are trying to see whether the data that gets generated is structured data or semi-structured data or unstructured data. We also know the definition here. Structured basically means the data which is organized and also has data definition. We call it as schema. Semi-structured data which do not have schema, no readily available data definition, but the data is in an organized fashion. Right? It is organized. Hence, we will be able to manually give the schema to it. Hence, it's a semi-structured. Whereas when we talk about unstructured, there is no order or organized arrangement, and no schema. So even if you want to give the schema, you'll not be able to give it because there is no ordered arrangement. Then we've also look at whether the data is a big data or a regular sized data, right? Regular data. Regular data basically means the data which can be processed, which can be stored, which can be managed using the traditional tools and techniques. Whereas big data is a scenario, is a challenge which occurs when your traditional, when your existing tools and techniques will not help in resolving or managing that particular data. It could be from a storage perspective, or it could be from processing perspective broadly. Then we will declare that the data is a big data, and we are getting into a big data challenge. From a definition perspective, the core 3 V's, or the fancy 10 V's, 50 V's also there. Slowly we are getting more V's added to it. But the core is the 3 V's, which talks about volume, velocity, and variety. Right? So, excuse me. So these 3 V's define the properties of the data, and we will be able to define it as big data when we have challenge in these 3 areas. Now imagine we have this problem. Okay, you talk about any business. At the beginning, they don't have any issues. The data that is getting generated will be regular data. But as and how the business grows, directly proportionate is the size and the complexity in the data. Right? Data will also grow. This eventually becomes big data. Okay, any business. Okay. So what if an organization is growing overnight suddenly? Right? That is one problem. Now, for example, Amazon, if you talk about, right, which is the topmost e-commerce grocery company, e-commerce right, company, world's popular. And it is said that there are more than 2,000 transactions that happen on Amazon. Okay, there are more than 2,000 transactions that are happening in 1 minute across the globe. So you can see the size of the data that we are dealing with here, the speed at which the data is getting generated. And if I talk about the variety, the transactional data could be in structured format. You'll have predefined fields, tables will be there where the data gets stored. But along with that, we will also have product information, product specifications, right? The description of the product, the customer's feedback, right? So website content, basically, we are talking about. So there is a lot of unstructured data as well. So all the 3 V's are satisfying here, and this becomes a big data. Okay. So how do we deal with this big data as a question? So big companies like Google, Amazon, Microsoft, Apple, IBM, yeah, all these big giants had the biggest problem of managing the data. Google, for example, it is said that there are more than 2 million, not 2 million, I think I'm very, right? I think 2,000 petabytes of data will be processed on daily basis by Google. I think this is the correct number. I cannot recollect it, but yeah, this is something that you might want to cross check. 2,000 petabytes of data will be processed by Google every day. Okay, one day. We're speaking about just one day. They have to process so much of data. Right? If I talk about 1 petabyte, it is basically 1024 gigabytes is equals to 1 terabyte. 1024 terabytes is equals to 1 petabyte. So we are talking about 2000 into 1024 terabytes. If I multiply that with 1024, that is the amount of gigabytes, GB data that we are talking about. Now, where should Google store all this information? How do they process it? Now, you cannot have a computer, a single computer, which can store so much of data. Now, even if you say that, okay, fine, I have a server which can store so much of data, you might want to say that my server, Google is a very rich company, so they have procured a server which can hold 10,000 petabytes of data. Assume you have this kind of a server. Now, how many days will you be able to store the data in? Per day, you are getting 2,000. So in 5 days, your server is full. Then what you do? You again have to purchase another server, right? Even if it is, let's say, not petabyte, but exabyte. Assume it is exabyte. 10,000 exabytes, that is 1024 petabytes is equals to 1 exabyte. Okay. So this is the capacity of the server. Assume Google has procured that. Now, how many days we will be able to store the data in this particular server? Eventually, it gets filled up, right? As the data gets generated, it gets accumulated. Eventually, the server gets filled up. It cannot be used forever. Now, after that, what should we do? There's no other option to purchase another server. You'll purchase another server. Each server is going to cost a bomb, especially when you're talking about such a powerful machine. They are going to cost like bombs, right? So it's going to be practically impossible to keep purchasing these servers. Even for the companies like Google, it is not going to be practically viable solution. So how do we deal with this? What should we do in these kind of scenarios? Brainstorming was required. I mean, it's such a big data, we will not be able to manage it. If you are the customer and if you want to do some transaction, some Google search or anything on Google, then Google needs your past information, right? So where do we put that? I cannot keep deleting the old data because that is information. Past is very important for us. We cannot delete them. Every company had this issue, handling the big data that is getting generated. This is when Google actually came up with a white paper. They published a white paper. You understand the concept of white paper, right? Some research work, they are just publicly announcing that, hey, this is what we're doing. They wrote an article saying that how they started implementing solution to process their data. Because what happens is they have multiple such servers, right? So they have server 1, server 2, server 3, server 4, so on and so forth. Huge list of servers. Because once they fill up the first server, they go to the second server. That is filled up third server, fourth, fifth, sixth, so on and so forth. There's a huge repository of servers that these Google had. So now, if I had to process it, how do we deal with this? So what Google said is, they started writing a code. Okay, so Google said that we wrote a code in which we will first try and connect to all these servers individually, right? The code is such a way that it is going to look into the servers, individual servers, for the desired information. Because the data is keep accumulating on all these servers, right? All the past data is there in all these servers. Now, let's say you are a customer and you want to do some transaction on Google. So what they do, they connect. As soon as you connect as a customer, Google will be able to identify who you are thanks to your unique ID. So what did this customer do in the past? So using that ID, we will specifically look for the customer details in all these servers. This is retrieval. We are trying to retrieve the information that is available with respect to that customer. This is called as mapping. With respect to the customer ID, we are trying to map to these servers and get that relevant information. So once these information is available, all that will be accumulated. This becomes intermediate data. Okay, everything will be collected. And this intermediate data becomes the data for us to process, because all this is with respect to the customer ID. There are a lot of customers, all the data is not related to us, right? So for this particular issue, when the customer is logging in, only that customer's data is required. So we get the relevant data. We call this as intermediate data here in this concept. And once we get this intermediate data, which becomes relevant, we apply the logic. What is that this customer is looking for? We will try and do the processing on this particular data. So we are trying to reduce this entire data into results. We're trying to reduce everything into results. This concept was termed as map, reduce. First, map the information from all the servers and then try to reduce it to result. This was the logic which Google came up with, and they published it. Right? They said that, hey, this is what we try to do to process our data. This happened way back in 2004, friends. That is when the organization started to look into the big data and all that. And this is where the social media also came in around this time, early 2000s, 2003, 2004. That's when social media came in. And that's where your Google has transformed everything, like the entire business transformed, because Google does personalized analytics. And when people started being very active on social media, there's a lot of personalized information that was available. So organizations tend to store the data, started to understand the importance, and they started storing the data. Hence, they wanted to have more and more servers to accommodate that. But for processing, they did get this issue. Okay, so we are trying to map the information from all these servers. So first code, the logic says, try and get the data, right? That is map the data from all these servers. Now, once we get this, we will try and reduce that to the result. Okay, so this is basically a map reduce concept. Now, anyways, we are not going to deal or dwell into this process. Okay, but I'm just trying to give you the history on what exactly is the scenario. So Google had many servers. Let's say they are currently working on the active server, this one. All the information, old information is stored in these different servers. Now, once we get the data, we process it, right? So this is simple logic, very simple logic. This came up in 2004. So organizations who were having issues with storage, whenever we talk about data being too big, the problem will be storage of the data. You cannot store the data into a single server, and that is why we have multiple servers. But when multiple servers are coming into the picture, the processing becomes a challenging task. How will you process all the data which is stored in different computers? To solve this, Google came up with a solution, MapReduce solution. But there was still one more problem in this approach. That is, let's say you are using a server. Okay, this is your server. Not every company is as rich as Google. So if they want to implement this kind of a solution to handle their big data, they have to procure a very costly server. Right? So cost is going to be a big factor in these kind of scenarios. And suddenly, if pandemic kind of issues happen, let's say, for example, COVID-19 happened and Zoom, the link that we are connecting via, right? That software has become so much popular after the incident, right? After the pandemic, because everything became digitalized. So scalability is another problem. What I mean is, Zoom as an application, as a software, probably had 10,000 customers or 100,000 customers before COVID. But after COVID, billions. That means suddenly in a month or so, the entire Zoom's business has multifolded, suddenly become like boom, right? So that did Zoom plan for these kind of pandemic kind of issues where their business is suddenly growing to an extent where there will be too many challenges to store, process the data, right? Scalability. So they have to keep purchasing the servers. They have to be ready for all these things. That was another challenge, scalability. Now, what if this server, assume for example, what if the server is a 100 terabyte server, capacity server? Your laptop probably will have, okay, let me say petabytes, okay? Your laptops probably have 1 terabyte storage. Let's assume that we have 100 petabyte server. That is 100 into 1024 terabytes. So if this is the case, and if your business is suddenly generating, right? So for example, Zoom, suddenly overnight, the number of transactions that have happened is more than 100 petabytes. Just in one day or 2 days, or maybe in a month time, we are getting more than 100 petabytes of data. So I cannot store everything here, right? So I need to purchase a server. Now assume pandemic happened and in one day, in one push, one flush, we get 1,000 petabytes of data suddenly. Now, can I store all this data? Let's say this is a single data bulk load that we are trying to do. Can I store it in this? It's 100 petabyte storage device. That means, in simple terms, if I have to explain, assume your laptop has 1 TB storage space, disk space. I am giving you, let's say, 2 terabyte file. I want you to store. Will you be able to store a 2 terabyte file in a 1 terabyte hard disk? Can you do that? Not possible. We cannot. Physically, the system is not capable to store that. Now, this was the biggest challenge in implementing this solution. This is where a software called Hadoop came into picture to solve this purpose on top of MapReduce. Hadoop. In 2005, two people, Doug Cutting and Mike Caffarella, I think they were working in Yahoo, I don't remember, but yeah. They came into picture and they said, why not use multiple servers all at one time rather than keeping one server active, using that, and once it is filling it up, right? Once it is filled up, keeping that as archived server and then taking new server. Rather than doing that, why not use all the servers together? So this concept was slightly tweaked. So what they did is, I'll erase this part. What they said is, let us have all these multiple computers interconnected. Okay, this is basically what we are looking at, multiple servers. So I'll have server 1, server 2, server 3, server 4, server 5, server 6, server 7, server 8, server 9, 10, 11, 12. Okay, so 12 servers are interconnected, but all of them are active. Every server can be utilized. It is not filled up. New servers, I'm interconnecting them, right? And I'm creating a cluster. We call this group of computers interconnected, a LAN, right? A network as cluster here. And they said, if I have a file, a data, which is having a capacity more than what an individual server has, right? That is the actual big data problem from a storage perspective, right? So we wanted to solve that. So what they did is, assume each server is 1 TB, like this. So in total, how much storage I have? In total, I have 12 terabyte storage. If I add all the storage spaces, I would be able to get 12 terabyte storage space. Now let's say I'm giving you a 3 terabyte data, 3 TB, or let's say 5 TB, right? Anything. A single data file. I cannot store this entire TB, 3 TB in one server. That's not possible. So what we do, the concept of Hadoop says, split this data and then store. For example, this 3 TB is getting split into 3 different 1 TB files. And this data is getting stored in these servers. Data partitioning happens here. So we split the data and then store it. Now I don't have a problem. Rather than a single computer, it is always good to have a cluster of computers helping each other, working in tandem to solve the big data problems. Right? So this is called as Hadoop, and it basically uses a concept of HDFS. H stands for Hadoop. DFS means distributed file system. And it also has map reduce, which is obviously the concept of processing, which was defined by Google itself. So for processing the data, we will try and split the job into 2 parts. One part will try and get the required data from all these different servers, and the other part will actually do the processing. Whereas HDFS component is going to split the data and allow us to store the files, store the data on different systems. So Hadoop can be seen as an operating system. It is a software which can be handled as an operating system. So for an end user, we are looking at a single big powerful computer which can have 12 terabytes storage space, 12 processors. Even if I talk about a single processor machines, each of this is a single processor machine. I have 12 processors, right? So I will be able to do the processing by distributing the tasks to all these 12 processors, and the data is getting stored, right? So 12 TB data can be stored. This is the concept which was enhanced and cloud came into picture. AWS, Amazon Web Services, it came into the picture around the same time, 2005, 2006. Yep, so there you go. This is called as distributed. Yep, this is called as distributed framework. All right. Any questions? Whatever we discussed till now. Do we have any questions? All right. So next, in the right organizations, people started using this big data. Oh, give me a minute, huh? Just give me a minute, please. Yeah, some background noise. All right, so we basically started using, when I say the industry started using Hadoop. It has two components to start with, but later on, these two components became three components. One is the HDFS. This component is specifically used for storage purpose. I mean, the server will ensure that the files are split and then internally stored in different physical systems. Then we have MapReduce. This is the concept which allowed us to do the processing. And then, because we have multiple computers, we call them as nodes. In a cluster, each computer is called as a node. So because we have multiple nodes, we needed some service which can actually control all these particular nodes. So for that, there was another concept which was developed, which is called as YARN, yet another resource negotiator. So in Hadoop 1.x, only these two were there. In Hadoop 2.x, latest versions, later on versions, we had YARN, which was introduced. This is cluster manager, managing all the nodes. These are the three services which were developed in Hadoop. Okay, now the problem with this concept of Hadoop is that it has very high latency. What does latency, high latency means? Exactly. High latency basically means it takes a lot of time for processing, time to get results. It is a high time. So it takes a lot of time. This is because the processing which is happening using the concept of MapReduce is a batch processing concept. Okay, so what happens? In this cluster, the data, when we want to store some data, it gets partitioned, right? And then stored in different systems. Now, when you want to process it, we will run map jobs to start with, which basically try to retrieve the information. Now, the data that we are trying to retrieve is stored on the disk storage space. Okay, individual disks files. So, for example, I have one file, which is 1 TB. I'm splitting this into 250 MB, sorry, GB, my bad. 250 GB. Assume, theoretically, we are talking about the partition here. So each of this file goes and sits in one of these servers. Now, within this file, there will be a lot of columns, lot of rows. Map job will try to go through this file and get only the data which is required. So we will run a query, map reduce, right? Is basically the map job is basically to retrieve the information by doing the queries. So it needs to access the disk. So disk input output happens. Every time when we are trying to access any record, any information, we will have to access the disk storage space of that particular individual computer, individual node. Now, whenever we write these kind of queries, right, whenever we are trying to access the disk, because it goes to the disk for retrieving the information, the process becomes very slow. Disk read and write operations are always slow. Okay, disk read write operations are slow. Remember this. So Hadoop is slow. And on top of that, we are also dealing with very big data, right? Large amount of data. So Hadoop has this high latency issue. Now, how do I solve this specific problem? Yep. So there were many solutions which were tried to be developed, but ultimately Apache Spark came into the picture. And this Apache Spark revolutionized the way how this cluster is being used. Okay, so we are going to talk about how your Apache Spark can allow us to do the processing of the data which is stored in this distributed framework. Okay, that is the concept here that we are trying to understand. So let us try and unfold the things with respect to Apache Spark. I just gave you very, very high level information about Apache Hadoop. We are not detailing anything there. It is the scope of this particular session does not deal with Hadoop. We have to talk about Spark. But just to give you the background on what exactly distributed framework means, I explained the background of Hadoop. Okay, there might be a lot of technical questions. We are not getting into those details at this stage. So yeah, these are some of the concepts that we will be talking about. And you can see it is all focused on Spark only. So if I go to the history of Spark, Spark was developed way back in 2009, started developing in 2009. Okay, and this was in a lab of a university, UC Berkeley University. And later on, after 1 year, it was declared or it was given to the community. It was made open source. So Spark is open source. Okay? That means everybody can contribute. That's the point there. Of course, Hadoop was also open source. Hadoop was developed using Java software. Okay, whereas Spark is used. Spark was developed using another programming language, something called a Scala, which is very similar to Java. And of course, it is similar to Python as well. Okay, so that's basically the source which was used, the language which was used to develop Spark. I'll talk about that anyways. So Scala was used, but it was declared as open source in 2000. Now, as soon as it was launched, right, it was in the market, it was given to the community. It became the largest open source software communities in the big data area. Right? Because of its capabilities, because already organizations were transforming into the world of big data, and they started using the concept of Hadoop, but they knew the challenges, right? It was becoming very slow and all that. But to overcome that, Spark was actually allowing users to do the processing, and that is one of the reasons why it became very popular. Of course, there are other benefits, other features, which also keeps Spark always interested. Interested among the users. You can go to this particular website, and we'll also go there. You'll also be able to see the contributors and all that history if you want. You can just experiment, explore this website. Next, the Spark, right? If you look at this, Spark is a tool for interactive and multi-step analysis tool on Hadoop cluster. So Hadoop is a distributed environment, right? So that means we will have multiple computers which will be interconnected together so that they are working in tandem. And Spark is working on this particular cluster. We call it as a Hadoop cluster. Okay, yeah. So Apache Spark is a tool for interactive and multi-step analysis on a Hadoop cluster. This is a very, very high-level definition. If you read this and try to understand it, it basically allows us to understand the capabilities of Spark in this paragraph. How does MapReduce job work? MapReduce job basically will have two functions. Map jobs, map functions, and then reducer jobs or reduce functions. Map task and reduce task. Map task is a retrieval. It's a task to retrieve the relevant information from multiple servers which are interconnected in the cluster. So in this retrieval process, Hadoop takes a lot of time. Why? Because the data is lying on the hard disk of individual computers. Right? If I have a 1 TB file, we are saying this will be split into 250, 250, 250, 250, 4 files. So let's say the file is stored on this hard disk, this hard disk, this hard disk, and this hard disk. So when we are trying to access, we will go to this individual file, this particular server, look into that particular data, and then retrieve the information. But ultimately, it stores on the hard disk of the server. So hard disk gets involved, and this is the reason why the process becomes slow. Now, what this concept of Spark does is, it uses memory. Okay, it uses the memory of these computers, RAM. So when the data is there on the memory and not on the disk, then obviously the processing becomes faster. The speed at which your hard disks work and the speed at which your memory work is very, very different. And more the RAM you have, more the speeds you'll be able to achieve. And Spark is a concept which started using the concept of memory. Okay, so that is the reason why it becomes very fast. From a features perspective, or from a definition or concepts perspective, Spark is a fast, interactive, in-memory cluster computing framework. We'll be able to process the data using all these features. Okay. And Spark specific design was to ensure that speed can be achieved and it can also scale up. Okay, it can also scale up. Scale means you probably will use more resources if required. You can just increase, like Zoom's example I have given. Now, it has libraries, or you can say APIs, which allows us to connect with various data sources. What are data sources? What does data sources mean here? Data sources basically means the softwares which are designed to store, or you can also say archive, and manage the data that is getting generated. Store and manage the data. These are nothing but database softwares. And the most popular software are RDBMS softwares, right? Relational database management systems. These are the primary, very, I should say, widely used software. And we will use SQL language to deal with the data which is stored in the softwares. Now, there will be various other data sources also. This is just one example I'm giving. So Spark has the capability to talk to all these various database softwares or any other sources of the data. Right? Readily available plugins or integration steps are there, which will allow us to deal with the data which is stored in different softwares. It allows us to distribute and then process the data. Split. Distribution is nothing but split, because your data is, right, your infrastructure is allowing you to split. This is my cluster. Right? So if I have like this cluster, then my processing can also happen by taking the advantage of all these individual servers that we have. So distribute and then compute. And yeah, this is the point which keeps it different from Hadoop. In-memory computing framework. So if I have to summarize the way the Hadoop and Spark work is, if this is a cluster, and if this is a Hadoop cluster, each computer is a node, okay? We use the terminologies. Once again, I'm writing computer or server or a machine or a node. Okay, these are the names that we refer to. So if I have multiple nodes interconnected, then for the end user, we are trying to show the capability as the aggregated capability. So as an end user, we will see that this is a supercomputer. This is one supercomputer, which has the capability which is equivalent to the aggregated capability of all these particular nodes. Okay. So when I talk about the capability, Hadoop uses the processing capability. So I'll have how many? 4, 3, 12 processors. Hadoop will also use storage. So 12 into the hard disk size. Let's assume 1 TB. So I will have 12 into 1 TB. That would be the storage capacity. So Hadoop uses only these two. But how does a single computer, even if you're working on a single computer, how does the computer actually work? If I'm trying to, let's say, utilize any application, it could be any application, absolutely. In a single computer, in your local machines, if you want to start some software and use it, the software is actually stored on the hard disk, right? The related files and all that will be there on the hard disk. But you're actually processing it using your CPU, that is your processor, you can say, and the memory. Right? Anything that we try to process will actually happen over memory. But Hadoop is not utilizing that memory concept at all here. So Spark says, why don't we use the memory of all these individual computers? Right? So that is basically the design of your Spark. So it says, let's assume every computer has very basic computer, right? So 8 GB RAM, assume. So Spark actually says, along with these two, we will also use 12 into 8 GB memory. 96 GB memory is there for this particular computer. So the storage is called as HDFS component. And the memory is called as in-memory, right? I mean, cluster computing, cluster memory. Distributed memory. So this is 96 GB RAM. That is the difference between Hadoop and Spark. Spark tries to take the leverage of Hadoop infrastructure or Hadoop concept. So on top of Hadoop, we generally use Spark. All right, so this is the overview of Spark. We will try and understand the various capabilities, the architecture of Spark and all that. But for that, we will take a short break and come back. If you have any questions, you might want to chat down those questions, then we will discuss. But again, focus on Spark. We will not divert too many things into Hadoop concept. Technically, there are a lot of things that we'll have to discuss, of course, to understand Hadoop. We're not doing that. Okay. So let's come back after the break, and then right, we'll continue. So it's yeah. We'll take a short break now. All right, friends. So we were discussing about distributed framework. The concept is basically very simple. We cannot solve the big data problem using a single server. If I have a single server, I will have challenge with storage. I will have challenge with processing. To solve the big data problems, we will have to also invest in multiple servers. So the challenges with big data to start with are, how do you store it? That's this point. How do you process it? The next is the cost associated with having the infrastructure. Right? This is also going to be another challenge. And then we will also have another challenge, which is scalability. You may be investing a lot of money and procuring a very, very big server. But is that server good enough if your business is growing beyond your control? Right? So that is another big challenge that we will have to look at. Hence, rather than using a single server, we will use a cluster of servers. That means we will try and take the capability of multiple servers by interconnecting them. This is called as a cluster. This is nothing but a network of computers. You may say that this is a LAN. Right? So we will connect all these computers in such a way that they can communicate with each other and work in tandem. This is called as cluster. And in order to utilize the capability of all these interconnected computers, we will have a software called Hadoop. So Hadoop can be seen as an operating system for this cluster. Operating system for this cluster where you'll have multiple computers internally. So this is my single computer, which will be managed by Hadoop. And we discussed that Hadoop has distributed file system concept. So it has a single storage, which is called as Hadoop distributed file system, which is physically nothing but the combination of all these individual computers. It's an aggregated, right, virtual storage space that is created so that the end users can utilize that storage space. But internally, these are nothing but the physical storage of all these individual nodes. It also has the map reduce capability, which is basically the concept of splitting the work so that each task, subtask can be implemented on one of these nodes parallelly. And it tries to retrieve the data which is available on the disk. And then aggregated data will be used for getting the results, reduce task. And because there are so many computers, so many nodes, we also need some service which can control all that. So we call this as cluster manager, The name is Yarn, yet another resource negotiator. These are some of the things that we discussed. The disadvantage or the one of the drawbacks of Hadoop is that it does not utilize the memory of the computers of this entire resource. This is where Spark comes into the picture, and Spark says the processing will be done using the memory of these computers, distributed memory. Okay, so that is the concept of Spark. That's all, very simple. But how does this actually happen? And right, what are the various points that we need to look at? There are some more points, just a quick high-level information. Spark is said to have 100 times speed compared to any of the MapReduce work. Because MapReduce, right, it simply uses hard disk. Whereas when we talk about Spark, it uses memory. So there is a huge difference in the performance, and Spark is said to have 100 times speed when compared to this MapReduce when the data is stored in the memory. Okay, so whenever you are trying to access or whenever you're trying to process any data, at the first step, the data is actually on the hard disk only. In Spark, we try to move the data into memory, and then the processing happens in the memory. Right? So first iteration, even then, because the processing is happening in memory only, it is said that Spark is 10 times faster than your MapReduce related work. So it is still speed, right? There is still speed. But of course, there is some kind of arguments on this benchmarking. And when we talk about the iterations that continuously happen, the consecutive iterations, right? First time, yes, disk is getting involved. But once the data gets stored in the memory, then you don't have to access the hard disk. Directly go to the memory, the data is already there, and you process it. So because disk is not at all coming into the picture, it is said to be 100 times faster. And Spark is a thread-based application, just like Java. It uses threads concept, your physical computers, right? Hardware. So it uses the threads which are there in your computer for assigning the tasks and processing it. You can imagine thread as a processor, okay? Spark uses JVM. The people who are coming from Java background, you understand what is JVM, right? Java Virtual Machine. Using this, we try to execute the transactions. And Spark has one JVM per machine. Okay, one executor. And this executor can process multiple threads at the same go. If your processor has multi-threads, then all those multiple threads can be parallelly executed or used for executing your tasks. And within the threads, we can have multiple subtasks. So you can, if I have to draw it in a very, very high level, right? So this is your JVM processor, you can say, which processes the tasks, right? So here we will talk about threads. I'm drawing only 4 as you. Each of this thread will have again tasks. So here we can have parallelism, here we can have parallelism. Right, so you can imagine the level of parallel computing that we can achieve using Spark in a single computer itself. And we're talking about multiple computers which are interconnected. That is the reason why Spark becomes so fast. Next, you have to look at Hadoop as the operating system. Okay, so to explain this point, I'll try to map Hadoop with the operating systems. So Hadoop is an operating system, just like your Android. Android is also an operating system, open source operating system, which is given by Google. Everybody understands, right? You use your regular mobile phones, Android-based smartphones, right? We're using those smartphones. So in your mobiles, you have a lot of softwares, mobile applications. All these mobile applications are available in Google Play Store. Whenever you want anything, you will install, right? Hundreds and hundreds and thousands of softwares are there for Android operating system, correct? Same way, Hadoop is an operating system which was given by the two people, which was developed by two people, and it is open source. And on top of Hadoop, we also have different softwares, applications, which can be used on Hadoop, just like how we have mobile applications being used on Android phones, Android software. So try and map it, okay? So Android is like your operating system, right? So same way, Hadoop is your operating system. So we call all these applications that are available, which can be used on top of Hadoop, as Hadoop ecosystem tools, right? This is a Hadoop ecosystem, like your Play Store, Google Play Store. Same way we have Hadoop ecosystem, in which we will have hundreds and thousands of softwares. All the softwares that work on Hadoop, they go for map reduce logic only, because your Hadoop is designed that way. But Spark is different. And that is the reason why we are also specifically talking about Spark. Right? And when we talk about MapReduce uses disk. For processing, it uses hard disk. And because of that, there is high latency. To overcome that, we use Spark. So you might ask that question, so I'm upfront giving you the answer. Why Spark when we have hundreds and thousands of Hadoop ecosystem softwares? Spark is special, which reaches higher speeds. So benchmarking and all those things were also done. A lot of comparison was done with respect to Hadoop. We'll try and see those slides also. But just to summarize the features of Apache Spark, you can see all these here. It is open source, it is distributed and parallel computation capability, right, is also there. In-memory computation happens, so it is using memory. It allows us to do iterative work, specifically designed for iterative work. Repetition, because once you are doing any task, the data goes and sits in the memory. And if you are repeating the same task, then you don't have to go to the disk. Data is already there in the memory. So Spark is specifically designed, if you ask me, for iterative works, repetitive works. Then we also have interactive applications like Python. We all are familiar with Python, right? Interactive mode, scripting mode. So Spark allows you to do interactive programming. Then it works on distributed data sets. Distributed data sets means the data is split and stored physically in different computers. In the network, we are using multiple physical computers to store the data. Okay? We partition the data and store it. So it allows us to deal with that data also. Hadoop is only a batch application mode software. MapReduce can only allow batch mode operations. That means offline data operations. Whereas Spark also has real-time application capability. Live streaming data processing can also be performed using Spark. Then this is the beauty, friends. This is what we should be really thankful of. Spark is not a programming language. Spark is a platform. Like Hadoop, which is an operating system, Spark is also a framework, a software, which creates a kind of a platform or you should say a framework on top of which we will be able to use different other softwares for doing the programming. And it allows Python, Java, Scala, and R programming. It all started with Scala, right? It is written in Scala programming, also known as hybrid programming language, because it has both the capabilities, function-oriented and object-oriented like Python. And it is just like Java. From an object-oriented perspective, it's just like Java. Your Scala programs, when you want to compile and execute them, it creates Java class file zone, Java bytecodes. And it is also like Python, functional-oriented capability. So those two are also supported, and R is also supported, and Spark also now supports SQL. Of course, from the beginning, Spark was also supported SQL programming. So these are 5 different options that we can use for processing our data in Spark. Now, for processing your data and for storing your data, Hadoop uses multiple computers. All these computers can be commodity hardware. When I say commodity hardware, regular hardware, something we use as an end users, right? You don't need to have a specialized servers. If you are purchasing a single server, then yes, you need to have a super powerful server. But when you're trying to use a cluster, we are trying to use regular hardware, combine the capacity of all these individual computers to create one super server. Right? This is what Hadoop allows us to do. And when you're using Spark on top of Hadoop, you're using commodity hardware capabilities. Fault tolerance and scalability are another 2 features. Scalability means you can grow up. For processing, you can take more memory, you can take more processors, right? All those things. It's very simple. Plug and play kind of an architecture. So in Hadoop also, we do this. You add 3 more computers, your cluster capacity becomes more powerful. Depending on how much resource you want, you keep adding or keep removing the services, servers. Fault tolerance means even in case if one server's application is failing, one server is failing, then the application does not die. The overall application does not die. The failed transaction or failed task can be implemented using other tasks, other processors. Okay, so this is basically the data processing tool. So all the people who deal with data can use Spark or are using Spark. Now, one thing, Hadoop was initially developed to work on Linux operating system. Of course, it also supports Windows, but ultimately the file system will be converted into something which is Linux file system. We call that as XFS, extended file system. For Windows, we will have NTFS. But this is not supported for distributing. It's already distributed. We cannot further distribute. There is XFS, which is the Linux operating system, file system. It has the capability. So Hadoop was originally designed to work on Linux operating system only. But Spark, it can be used as a single standalone processing unit as well. And we will be able to use the software either on Windows or Linux, no problem at all. And we'll support both operating systems. Right. So this is basically the features of Spark. So Hadoop, as I said, right, it was launched around 2004, 2005. Prior to that, there was no solution at all to handle big data. Right, so Hadoop came into the picture. It revolutionized the entire industry on how do we process the big data. But the problem here is in Hadoop, we will be using MapReduce framework, which is also a low-level programming abstraction. That means we needed specialist programmers to deal with the development. Any code that you want to develop in Hadoop MapReduce framework can be done using Pascal, Java, right? C programming language, these kind of low-level programming languages, object-oriented programming languages. Right? We can also use Python's object-oriented capabilities to design the MapReduce codes. But as I said, we needed programmers, specialists. So functional people will be there, programmers will be there, right? Combination of these two resources efforts are basically giving us some results. Two different resources, so there will be always right misunderstanding and all that. When I say misunderstanding with respect to the technical capabilities of these both resources, communication gap will be there. So the end result will not be as effective as we wanted. And thanks to Hadoop's upgrade into Hadoop 2.x, where Yarn also come into the picture, it allowed people to start developing their own applications, like Hadoop ecosystem I just mentioned, like Android. Different organizations, different people started developing different applications like this, so that they can use these applications to get their work done. Internally, these applications will change the code to MapReduce only, but as an end user, you don't have to write everything in the low-level programming. Non-programmers, functional people also started taking the advantage of these applications. But practically, the problem is for every different task, we will have different application. Now, if it is a mobile phone, then fine, it's for entertainment. But if we talk about Hadoop ecosystem dealing with data, then different organizations have different requirements, different capabilities. So it was not practically, again, easy to utilize this Hadoop's capability. For example, if I have a project, a specific project, I will be using one application. If I have project 2, then I'll have to use another application. The requirements will be completely different. Maybe project 3, third application, 4, fourth application, so on and so forth. If this is the scenario, then the problem is you need resources, right? People who know these different applications. So people have to learn all these different applications. Hundreds and thousands of different applications are there. Right? Or you give time to the existing resource to learn these different applications and then become expert to take up the project. Either hire or give the training. Both are time consuming and very costly, right? Application, costlier solutions. So when Spark was launched, right, it became very popular in 2014, though it was launched in 2010. It was made open source in 2010, but it became slightly popular from 2014. Okay, Spark. It is also called as unified engine, generalized unified engine, because you need to have a single software to do many things. You don't need so many different applications. Right? So if you are capable to handle Spark, then job done. You'll be able to do many things. Right? So this is also another reason why Spark's becoming popular. So if I have to compare between Hadoop and Spark, then as I said, Hadoop has these three components. Map reduces for processing. This is cluster manager. This is to manage all the resources that we have in the cluster. HDFS, this is the storage component where the data gets stored. If when I compare Hadoop with Spark, the processing component is the only thing that we will actually start comparing. So Spark is a computing framework which is comparable to MapReduce. Spark does not have any competition for Yarn, or for that matter, Spark does not have a storage component. So we'll be using Hadoop HDFS. Right, so this is the comparison. This is the only thing that we will basically try to compare. And with respect to Hadoop, we have different applications, whereas in Spark, software is same. Within that, it has different capabilities. It's not a separate software. It is the same software. It's just capabilities vary. These are different modules or different libraries, you can say, in Spark that we will be using. This is the comparison. Hadoop, it has both storage component and computing component. Storage is HDFS. This is MapReduce. Whereas in Spark, we are only talking about compute. There is no storage component at all. Any application that we talk about in Hadoop, it uses MapReduce framework only. The way the processing is done is using this MapReduce capability, where you will try to retrieve the data and then apply your logic to solve the result from the data. Whereas Spark is a generalized computation. There is nothing like you retrieve the data from here and then do the processing and all that. Right? It is called as a generalized computation. Data will always be there only on disk. In Hadoop, we don't have a memory concept at all. So everything will be on disk only. But Spark's capability is the memory. But initially the data will be on the disk only. But right, when you have to process it, the data goes from storage device to the hard disk to memory. Hadoop is not designed to iterative work, because every time it wants to process the data, it has to access the hard disk. So it's not ideal. Especially machine learning kind of a task will not do it on Hadoop. But Spark, it is specifically designed. It is very good with iterative tasks because data will be there in the memory. Hadoop can only do batch processing. Here it can do real-time processing also, and the speeds are also very fast, 100 times. Here you will have to use low-level programming abstractions, whereas here we will be using different capabilities. You don't need to stick with one specific capability. We can have different programming languages capability. And when the benchmarking was done, right, you can see Hadoop has a world record. It created that record. When we wanted to process 100 terabytes of data, 100 terabytes, right? In those days, in early 2000s, there was no mechanism to process this data. That it was only the traditional way to process, and it used to take huge amount of time, days together. But when Hadoop came into the picture, and when the benchmarking was done using 2,100 computers which are interconnected, When the data was processed, 100 terabytes of data was processed using these 2,100 computers. It took 72 minutes. It's just about 1 hour, that's all. So that was the world record then. But when Spark was introduced to process the 100 terabytes of the data, when benchmarking was done, it was observed that it only takes 23 minutes to process that. And that too, the number of nodes is 10 times less. 2,100 compared to 206, or you can also say 210. So the time it takes to process this is drastically coming down from 72 minutes to 23 minutes. Right, so that is the advantage. Okay, so this is the benchmarking. And of course, this is the reason why we want to take the advantage of Spark. Now, this is the flow which we already discussed. So HDFS, this is your disk. Data is there on the disk, right? So data is here. So IO happens. When I say IO, I'm talking about disk IO happens, read-write operations. And we are running map tasks. Yeah, we are trying to run map jobs. The retrieval process will give us key and value pair data. We call this as intermediate data. So again, you're storing that in the disk itself, right? So once the retrieval happens, we need to store those data points on the disk. So again, you're reading and writing the data onto the disk. So in fact, here you'll read, here you will write. Temporary location, but it is ultimately on a hard disk. Then again, we will do the read-write operations. This is to read this intermediate data so that we can apply reduce applications and we'll get the results. Now, those results should also be stored on the disk. So again, I will have the write action. Right? Ultimately, it goes and sits on the disk. So how many disk read-write operations are happening actually here? 4 disk IO operations happen. Next, if I try and compare this with the Hadoop, right? I mean Spark, Hadoop versus Spark. If I try to do it, the data will be there in the disk itself. To start with, data is here only. Okay, so this is your disk. And the disk IO is happening. Here we will do read operation, but this read operation is going into the memory. Now, once the data is in the memory, the processing happens. Spark task will be executed here, task 1. So we're not accessing disk for doing the processing. We are accessing the memory to do the task execution. And the executed result probably will have to store. Again, I'll be keeping that intermediate data in the memory itself. We are not going to store that into the hard disk. It's a temporary data, right? I mean, temporary results. So it will be there in the memory itself. Now, on this particular intermediate data, maybe we will have task 2 to take care. And I'm doing this. Here again, we will have disk IO. Now, the results that we are getting, we have an advantage where we can directly show the results to the end user. You don't have to store it. It can be there in the memory and you can just show the results. Or if you want to store it, then you can go to the disk. Right? Disk I/O happens only when you're trying to write the data onto the hard disk. So if you see mandatory, only one disk I/O happens. The second disk I/O app is optional, but whereas here there are 4 disk I/O operations, input-output operations. So this is the flow, and this is because we are eliminating the disk access, the overall process becomes automatically much quicker or much faster. And when we talk about architecture, this is what happens. We will have something called as master-slave architecture. Master-slave architecture for any distributed framework-based software will have this master-slave architecture only, including Hadoop. This is because we will have many such computers interconnected. So there's a team which is working together, right? And in the team, if you don't have a manager, then the entire team becomes chaotic. Right? There will be no order, no effectiveness. So any distributed computing based or distributed framework based software, it will always be master-slave architecture. This is your master and rest are slaves. If I talk about Hadoop, the master is called as name node and slaves are called as data nodes. This is Hadoop's terminology. Whereas in Spark, the master is called as Spark driver and slaves are called as Spark worker jobs. Right, so this is basically the architecture. We will have a single master and many worker nodes. So what happens is when we have a task, let's say an application, we are doing a task or we're running an application on Spark, we want to execute few things. So the master program, that is your driver program, will take the task, analyze it, and understand what resources and all those things are required. So it communicates with the cluster manager. In Hadoop, we have YARN. In different services, we'll have different cluster managers. If you're using Spark on top of Hadoop, then this is YARN. So we will have YARN, which actually keeps the information about all the worker nodes. So driver program will learn about the current status of all the worker nodes using the cluster manager. And then from that information, the master program, that is driver program, will assign the tasks to the worker nodes. And on the worker nodes, the actual execution will happen. Okay, this is the diagram. And if you want to visualize this at a high level on how the flow happens, then this is basically what happens here. We can see master, the end user is giving the application. They're trying to get it done. So this task is getting subdivided into multiple subtasks. Each subtask is then handed or given to the slave nodes or worker nodes. On the worker nodes, the processing happens, and then the results are returned back to the master, where the aggregation of all these results will happen to show to the end user. So typical flow of your Spark job. Now, Spark is called as a unified engine because it has many capabilities which are shown in this particular slide. This is the entire, you can say, architecture. It has primarily Spark core component, and then these 4 other modules, which basically allow us to process different types of requests. And at the user level, we will be able to, end user level, we will be able to communicate with the Spark application or Spark software using one of these programming interfaces. It does not have any storage component, so it allows us to actually connect with different types of data. Okay, and Spark does the computing in memory, so it really does not require the structure and all that. Right, so we will be able to process unstructured data also using Spark framework. So if I have to talk about individual components, then yeah, this is basically how it goes. Spark core. This is the core component. Spark contains the basic functionalities, and this component will actually enable us to do the memory management, fault recovery, interacting with various resources, and scheduling those executions. Right, all these things happen at the Spark core level. Spark core is very, very important because it also allows Spark to read and understand the data that it has to process. Okay, and this component has an API which allows us to do that. This is nothing but your RDD. When Spark was launched, correct? When Spark was initially developed, the only data that Spark used to understand was RDD, which is a memory object. Right? This is like an object which is stored in the memory. Okay, memory object. But now Spark also supports data frames, right? Or tables, you can say. It's nothing but data frame is nothing but a Python data frame kind of a arrangement. It's a table, structured arrangement. Then if I talk about the SQL, Spark SQL is basically the package, just like you have Python packages, same way we have this package or feature, which allows us to work with structured data. Right? SQL is always about dealing with structured data, right? So if your big data has structured data, and or if you want to deal with the data in a structured format, then yeah, Spark SQL comes into the picture. Spark streaming, any real world, right, or real data that we want to, live streaming data that we want to process, then we will be able to do so using the Spark streaming capability. Then machine learning library, this is one of the reasons why Spark sees a lot of users, because machine learning is an iterative task, right? And Spark was specifically designed to deal with these iterative kind of tasks, right? So machine learning experts generally will be seen using Spark for machine learning capability. Then graphics. Graphics is a library which is basically designed to manipulate the network graphs, air traffic, social media network, right? So these are all examples of cases where you will have interconnected nodes, right, like a graph, and you want to process that graph. In Python, we will have network X library, which is basically used to process the graph data. In Spark, we have graphics. Then comes the interaction. In order to type your code, we need some kind of a platform. And Spark is just a software which allows users to use the capability of the resources and the distributed memory to process the code that they are writing. But different programming languages that we are talking about, we have discussed about 5 different programming languages. Each of that, when you want to write it, needs some interaction, right? Some kind of an interactive medium. That is nothing but Shark shell. The Spark shell is like your command prompt. Okay. And if you're using Scala, we will have Spark shell. If you're using Python, we will have Python console. For Java, we don't have any such interaction. For R, we have R console. Right. So these are the Spark shell related details. It's basically nothing but a place where you are going to type your Spark codes. Depending on, again, your programming language and its capabilities, we will choose the appropriate interactive medium. Next comes the important point, the Spark's building blocks. This is probably the last theory bit that we will be discussing. And post this, we will try and install Spark in Windows and then start using that Spark as well. But let me talk about the building blocks first here. When we talk about building blocks, these are basically the 3 entities which are responsible for us to eventually develop Spark code. So how we utilize Spark's capability for processing anything, right? So there are 3 important entities that we'll have to understand: Spark context, RDDs, and the operations. So what does this Spark context means and what does this RDD means, right? So let's try and understand that, starting with Spark context. If you look at the definition, it says it's the heart of the Spark application, is essentially a client of Spark's execution environment and acts as the master for your Spark application. It sets up internal services and establishes a connection to the Spark execution environment. Now, what does this mean? So if I have to go back, use this piece for drawing a cluster, Hadoop cluster, which also has Spark in it, if I have to talk about this. So this is my, let's say, Hadoop cluster where I also have Spark. Now let's say each computer has 1 TB storage. So how much total storage is there? 9 TB HDFS storage device. The cluster has 9 TB storage capacity. 1 TB. Assume each computer has 8 GB memory. So we're talking about RAM. How much is this? 8 into 9, right? 72. GBs. And then, of course, you have 9 processors. Okay. Yeah. This is the total capacity of your Hadoop and Spark cluster. Okay, Hadoop and Spark cluster. Now, let's say I want to do a Spark application, right? I want to execute this code using Spark's capability. Now, it's a one application, right? Task or one application. When you want to execute it, do you want to utilize 72 GB memory, 9 TB storage space, and 9 processors to process this task? Not required, right? It may not be required. So what we do is, we will take the resource from this resource pool. We will try to restrict, take the logical breakup of this particular software. Say, for example, I will need 1 processor. So from out of 9, we will dedicate 1 processor for executing this task. I would say, let's say from 72 GB, I will only take 12 GB memory. I don't require entire 72 GB memory, 12 GB memory. Right? Storage is anyways there. The data is lying in the hard disk. It could be any level of storage. So we are restricting the hardware resources for executing this application. We're dedicating and restricting, right? And dedicating this resource pool, from the resource pool, these set of resources that we are basically restricting for executing this task, right? This is called as your Spark context. In short, Spark context is nothing but the execution environment for a specific Spark application. Execution environment. Okay, so that's your Spark's context, the first bit. Now, once the task is done, then we are releasing these resources back to the pool. Or similarly, you will have different tasks, multiple different tasks. Then from this big resource pool, we will try to take different Spark contexts. Okay, so this is basically how your Spark context is defined or designed. It's an execution environment. And this execution environment, if you are running Spark on a local machine, a single computer, then you have 3 different options to choose from on how many resources or how much kind of parallelism do you want to achieve. Star basically says you can use as many logical cores that are there in your computer. You may not even know. For example, I don't know how many cores are there in my computer. So I'll simply say local star. It uses all the capabilities which are required. Then local K. K is the specific number of threads that you want to dedicate. If you are familiar and if you are resourceful to understand what number of threads you will have to give, then you will be able to give that. And if you say only local, then that means you are passing only 1 single thread. Sequential processing will happen. But we can also use the cluster managers. Right? For example, in Hadoop, we have yarn. Similarly, for Spark, we have Spark's cluster manager. And then if I have another cluster representation like called as Apache Mesos, that is a different software like Spark or Hadoop. If that is the case, then we will be able to use the Mesos cluster manager. So this way we will have the Spark context defined. You can see like this. Okay, so that is your Spark context concept. Now, once you have an environment, right, you want to use that environment to process. But on what you want to process? You need data also, right, to process. Now, that data to start with in Spark was called as RDD, which is nothing but resilient distributed data sets. This is the name, resilient distributed data sets. The resilient distributed data sets is like your memory abstraction. So if I have to explain this, this is my Spark cluster. These are multiple nodes that I have. The actual data on Hadoop is getting split and stored, right? So I'll have, let's say, 3 to 4 servers, which is having my relevant data that I want to process. So what happens is, when I want to process on that particular data, so I'll have a single file, but it is very big file for a single computer to handle. So in Hadoop, what we do, we partition the data and store those files in different computers like this. So assume I'm using 3 computers here, 3 nodes. So when I want to process this data, we will try to utilize the distributed memory. We will try and project this one file in the Spark context related memory that we have dedicated to this process. I said I'll use 12 GB memory, right, out of 72 GB. So this is the 12 GB memory space. So I'm going to store my data in that memory. Now, where is this memory coming from? Physically, it is from these computers only. So we are trying to store this data into this memory. So it's kind of a reflection of your entire data, which is there in different computers in the memory. But that memory is also actually physically different components, right? Different nodes memory. So we talk about the features of RDDs, resilient distributed data set. It is memory abstraction, right? Memory projection. So we can recreate it, right? So even if you are changing the data or deleting the data, physically it is not affecting anything in the system. Physical data does not get damaged. Right? And if your memory component is failing, we will be able to recreate it. So resilient. It cannot be damaged or missed. Distributed, of course, it's a straightforward definition because your data is getting split and stored, right? Distributed. So we are using multiple nodes in the cluster to have the data stored. Right? So this is your data. RDD. RDDs are distributed memory abstraction. Abstraction is like reflection or mirror image, right? So that is the definition. And because everything is in memory now, the entire data is in memory, we will be able to do in-memory computations. Okay, that is the definition or the explanation of RDDs. And there are many features. The most important feature that you need to understand is the data is read-only. So you'll not be able to actually edit anything once the RDD is stored in the memory, right? It is immutable. Your data can only be read. Even in memory, you'll only be able to read the data, the actual data. Any changes that you want to do, you can do that, but you'll have to store that into a different right, variable altogether. You need to create another object to store the result. Okay, so that is one point that you need to remember. Lazy evaluated. I'll talk about this lazy evaluation in the next slide, or probably when we take up the third building block, which is operations. It is cacheable because it is a memory object. We will be able to store the component or the data points for as long as we wish. Parallel processing happens, the partitioning of the data happens, right? All these things are different capabilities of your RDD. Inside the data partition, the data will be processed sequentially only. And it is consistent because of immutability. So you'll be able to use the data RDD data for archiving purpose and right, computing purpose from analytics perspective. It's not going to be costly affair. It's going to be very simple task. So from a computation perspective also, it is less expensive. Locality aware scheduling means your Spark cluster manager Spark, right, utilizes the information from the cluster manager to ensure that the scheduling of the task happens in an appropriate way where where the computers, the nodes which actually store the data will be preferred to process that particular data. Right? Data aware, data locality aware scheduling. Now, when we talk about RDDs, the RDDs can be developed using one of these right options. It can be parallelized. Parallelization can happen, and this will convert your existing object, which is in memory maybe, into Spark object, Spark's memory. Dedicated fixed memory component will be there. So you're going to store your object into that Spark context related memory. Parallelize it. Then we can directly store the data into Spark's memory from a physical file. Or we can create RDDs if you already have another RDD. So when you do some manipulations on RDD, we will get the result. That result becomes another RDD for us. Okay, and the only two things that we can control with respect to Spark is how many partitions you can do it. Logical partitions, by the way, because the data is in memory, right? So we want to logically partition the data so that we can use those many processors to or threads to achieve the parallelism. And the other one that we can control is how long you want to keep that particular data stored in the memory. Now, Spark, when it was initially developed, it had only RDD support. That means the data has to be an RDD object. That means data which is stored in Spark's memory. And when it goes into the memory, there is no structure. In memory, we dump the data, right? So if I have some data in the hard disk, we just dump it into the memory. So schema is something that is not there in the memory. You just dump the data, right? So this is a scenario where your RDD will always or was always an unstructured data. But because it was very difficult to process an unstructured data, especially if you are dealing with machine learning related activities, the data has to be in structured format. Right? So later versions in Spark 2.x versions, the support for data, or I should say tables, came into the picture. Data frames, basically. Right? Especially the capacity of Python to do machine learning on data frames was brought into Spark as well. So Spark also brought support for your data frames or tables, SQL tables. Okay, so latest versions have the capability, not just RDD, but data frames and tables as well. All right. Now there is last point here. We will take a short break and come back and then discuss about the third building block of Spark, which is the operations itself. So we need the environment. We call this a Spark context. In the environment, we need data, and the data was RDD format. Or now you also have data sets or data frames, you can say, structured data. The latest versions also have the support for data frames. Okay. Now, once the environment is created and the data is readily available for your processing, then we will have to do the operations or executions. Now, what operations will you do? Right? So that is basically explained here. We'll talk about that in detail after the break. All right. So let us take the break now. So a quick recap after the break now. We are talking about Spark. And Spark is not a programming language, but rather it has to be treated as a platform or a framework. And the capacity is that it uses the memory for doing the computation. We call it as in-memory computing framework. Cluster computing framework, in fact. And in order to do that, of course, before that, we need to talk about the unified engine. It has different capabilities. The core component is the first component that we'll have to talk about. Then we will have Spark SQL. Then we have machine learning library, which has, we also have streaming capability, and we also have graphics. And in order to support all this, we will also have different packages which allow us to deal with all these different capabilities of Spark. And in order to deal with or develop any application on Spark, we will actually have to see its building blocks. So how we actually do the computation. In order to do this computation, first we need Spark context, which is also referred to as SC. Spark context is nothing but the execution environment. It is like the set of resources that we are dedicating for one application from the entire resource pool. We will have to define this, and post that we will deal with the data. The data, to start with, Spark used to only have RDBs. But later on, now we also have data frame supports. Then we now talking about what kind of operations we will be doing in this environment on the data. That's ultimately Spark basically talks about doing some operations. So what kind of operations we will be doing on this particular data? That is what we are trying to learn now. These operations can be broadly defined as two types. One is called as the transformations, also known as lazy evaluation. The other one is called as the eager operations, right? These are nothing but your action. Just give me a minute, friends. Sorry about this pause. Just a minute. Yeah, sorry about the pause. So I was talking about the operations. Broadly, these operations are categorized into two types. One is called as lazy evaluation. This is nothing but transformations. The other types are called as immediate or eager operations. We also call that as action operations. Now, how do we understand this? What exactly are these lazy transactions or transformations? And then what are eager operations? Now, if you want to understand this, right, let's go back to our childhood days. A typical childhood, right, days, especially in India. This is how our childhood has passed, especially in summer vacations. So I'll take one small example here. In summer vacation, we generally, when we were kids, school-going kids, we used to enjoy the time lazily lying on the couch and watching the television, right? Let's say one such afternoon, you're lazily lying down and watching, let's say, television. Your mother is trying to prepare something for you, and she needed some help. And one of the craziest thing that we as children in our childhood days were supposed to do, especially Indian kids. Can anyone tell me what is the task in the house that every kid was supposed to do? Yes, filling up the water bottles, right? This is the example that I always try to give. Filling up the water bottles and placing them in the refrigerator so that we can have cold, freezing water. Yeah, everybody probably can remember that. Now, let's say this is your house. Okay, this is probably television. I'm just trying to be little, you know, kind of an architect here. So this is probably your sofa. You're lazily lying here and watching the television, and the water bottles are placed all these places, right? I mean, we are too lazy. We don't fill the water bottles. Now, probably your mother is in kitchen somewhere here, and she's preparing something for you. Now, there will be instructions. Instruction 1, task 1. Your mother from the kitchen is shouting at you to fill up the water bottles and place them, let's say, in the refrigerator. Now, what do you say? When you are lying here watching the television, what do you say? When your mother is shouting, what do you say? You acknowledge. Fill the water bottles. This is the task number 1. Do we get up immediately and do it? No. We only acknowledge. Right? Task number 2. She needs you to bring something which is there in the refrigerator so that she can use it for cooking. She's preparing something, right? So she asks you your help to bring that stuff into kitchen so that she can prepare it. Bring some stuff from, I'll write it like this, fridge, right? Refrigerator. Task number 2. What do? Do you immediately get up when she's shouting and asking you to bring it? Again, you're watching television by lazily lying on the couch. So you will say, yes, I'm doing it. Task number 3, assume. She's asking you to take something out from the kitchen and throw it outside probably, or give it to somebody else outside. So that means you'll have to go to the kitchen and take the stuff. Take the stuff from kitchen and go outside to dump it. Let's say dump it. Okay, go and dump it outside. So we have 3 different tasks. Now, when these instructions are coming, what you're doing? You're not completing it. You're still lying there on the couch. But when the instructions are coming up, you're acknowledging. That's all. Lazy evaluation. You're evaluating on what transactions or what tasks you have to complete. But do you get up? No. When do you get up? when there are some flying objects hit on your head from the kitchen, isn't it? When your mother shouts at final go and then throws something at you, that's when you get up. Right? That is your action. So immediately get up and finish the 3 tasks and go back to your position. Lazy transformations and actions. Now, if you would have been not so lazy, when the first task is assigned, what you do, you get up, collect all the water bottles. These are the water bottles, assume. You go to the filter, fill them up, bring them and place it in the refrigerator, go back. And sit in your position to watch the television. Task number 2, when it comes, you again get up, go to the refrigerator, open it, take the stuff, go to the kitchen, give it to your mother, come back and again watch the television. Again, the third task coming and you again get up, go into the kitchen, take the stuff, come out. Right? Come out and dump it somewhere. Now, what is happening is when you're doing these individual tasks from end to end, you are doing the same stuff again and again. You're repeating the job. You have to get up, roam the entire house to collect the water bottles, go to the refrigerator, open the refrigerator, put the water bottles, come back. Again, you go back, open the refrigerator, pick up the stuff from the refrigerator, go to the kitchen, hand it over, come back, again get up for the third task. So this getting up, moving here and there, opening the refrigerator, right? This is repetitive. Now, if you're lazy, then what you do? You're not immediately acting upon the task, but you are evaluating how you can do the task in the best possible way. You're lazy. You don't want to repeat things again and again, right? So what you do? You probably collect all the water bottles, go to the kitchen, right? Fill the water bottles, pick up the stuff that you will have to dump it outside. While you're on the way, you might want to open the refrigerator, put the water bottles, take this step back to the kitchen, and then come out with the stuff that you need to take. So the effort that you are doing is not repetitive. It becomes more efficient. Performance becomes better. Got it? So the combination of these two style of operations are used in Spark so that the performance is enhanced. Optimization is automatically achieved internally. So Spark takes care of that. Right? And there is one specific concept called as a DAG. DAG full form is directed acyclic graphs. Directed acyclic graph. Acyclic, that means you will go like this. It is not cyclic. It does not loop like this. Okay. Acyclic. So it will be like flow. It does not loop back. Okay. That is important. So this graphical representation will be created at the transformation stage. This is nothing but your plan. Execution plan, how you want to execute all these different transformation operations that you want to execute. It could be one transformation operation or multiple transformation operations. You are going to define this DAG, or Spark is defining this DAG internally, which is nothing but the best execution plan that we can think of. Series of transformations are there, right? So it basically defines the best possible way to deal with these things. Right? And then When the action operation is given, that's when this entire execution plan is triggered. This gives us the final result. All right, so this is how your Spark does the operations, transformations and actions. So Spark context, RDDs or data, basically you can say Spark data, and then Spark operations. These are some of the examples of transformations. We are not getting any manipulated results. Okay. We will do some kind of manipulations, but it doesn't change the data. Okay. We're not doing any calculations directly on the data, which changes it. These are called as transformations. Whereas if you talk about actions, it does some operations on the data and gives us the result. There will be an outcome in actions. There will be no outcome in transformations. Okay, and the workflow is like you'll have many transformation operations that you'll define, and then you'll have one action. When you execute this, all these sequence of transformation operations also get executed at one go. Until the action operation is given, there will be no execution. Only the plan is designed, that's all. So this is your Spark, friends. As I said, Spark is a platform, a framework, which allows us to do programming to process your data by utilizing the capability of the resources in the cluster. And specifically, Spark uses the memory concept for processing. All right, so this is basically your Spark concepts, theory concepts. Now I will try and explain how it can be installed on your local machine. It could be Windows. Mac, there will be a problem, you'll not be able to do it. Either you'll have to have Windows or Linux operating system for having your Spark installed. So let us try and do that on Windows system. Yeah, I've seen your question, Pradeep, Pawan, and this has been multiple times repeated and explained. These sessions are already there on your recommended video section if you're a registered student. Okay, the sessions are already there. All right. So let us now go into the Spark, Apache Spark download. You have to cross-check the entire resources. Do you have recommended video section? When did you join, Pawan? Let me address that point. When did you join the session, or when did you register for the program? Or you are recent joining? Okay, so you have recently joined. Do you see recommended section in your access? If you have that access, then you will have these videos. If you don't have that, then you will be given. You will be given the access, not to worry. Yeah, all the masterclass sessions, recorded videos will be there in the recommended video section. Okay. So yeah, you might want to just check with your representatives on when you will get the access for the recommended video section. I'm positive that it has to be closed, I think, today. All right, so let us come back to the discussion. Okay, so the website that we are talking about is spark.apache.org. Okay, I'll go to the main page, spark.apache.org. You can look at the website, and these are examples also given here. Python, this is how we can use Python. This is with respect to basic execution. This is an example of machine learning implementation, and this is with respect to your analytics basically. Then we can also do SQL related queries. You can see this is the select query, DQL queries. If you are familiar with SQL, then you know select queries. We have Scala. This is another programming language, which looks very similar to your Python kind of a execution. Very similar to Python. And then this is with respect to Java. And if you are familiar, then we also have R related example. So Spark supports these 5 different languages in its framework. And the most popularly used is Python via a library called Pyspark. Okay. If you are not familiar with Python, no worries. You probably will have to revisit this code and all that. You need to be familiar with Python to deal with Pyspark. Then we also have various other information, downloads, the libraries, documentation, very important examples, community and developers page also is there. We'll go to downloads to start with. We'll download the software first, and then we'll go to the different libraries and all that you can see here. So when you come to this page, you will see the option choose a Spark release. If you click on the drop down, you will have 32.x, 31.x, and 33.x, which is released in June 16th. 322 probably is an upgrade, and that upgrade came in July 7th. You can choose any one of these. These are stable versions, but yeah, see if it is recently coming up, then go one step older one. So June 16th is a pretty old one, so I'm taking this. We are in September now. So the latest version 3.3 is what I'm taking. Then along with this Spark libraries or Spark software, because Spark requires distributed framework, it needs certain libraries which are designed for Hadoop. So we will be using a package which is specifically pre-built for Hadoop 3.3 version, Hadoop software 3.3 version. You can also take the another option also 2.7, 2.x version basically, or you can also go to source code and all that. These are for more advanced people. We're not dealing with Scala, so we'll directly go for the first option here. You don't need to look into various other things, just select this two. When you choose these two in the drop down, you get the link here, download Spark. If you change this, the versions change. Okay, for example, if I say 3.3, the label is saying Spark-3.3. If I choose 3.2, look at that, the link changes. Okay, so choose that appropriate and click here. When you click on that link, it redirects you to this cloud space where you will have the downloadable link. When you click on this particular software, you will get the software downloaded. I'm downloading the software. It is 285 MB. Let it download. Almost there. I will go back here anyways. Yeah, the software is downloaded. Oops. Now I will take this software and place that in, let's say, yeah. Let me go to C drive. And you see here, I've created a folder called Spark3 under my C drive, or you can also put it in D drive. Any location is fine. I placed a folder called Spark 3, and within the Spark 3, I will bring the software. Okay, I have already installed it some time ago, and that version was 3.1.x. I'll not be upgrading it, but I'll walk you through with the steps here. So once you get this software, you unzip this. Okay, just extract it. Open with your WinRAR, or directly you can use the software to unzip this. Okay, you can say extract to the same location, Spark 3. When I do that, yeah, I get my software extracted. Spark 3 file, right? This one. Now I'll be using 312, this folder. Okay, you can use that folder that you have just extracted. Once it is downloaded, there are a bunch of steps that we will have to do. Okay, download, extract, place it in a specific folder. And within this, we will be doing certain steps. Okay, the first step that you will be doing is go into the conf folder. Right, there is a folder called conf. Open that folder, and here you will see spark-defaults.conf.template. After you download, extract, you will see this specific folder. You will have to make a copy of this file. It's a template file. So you'll have to make a copy of the file and remove the .template part here. And we will be editing this file. Just make a copy. I'll wait for you people. Once this copy is done, open this with Notepad. Open the file with Notepad. Not the template file, but the new file that you have, which is called as spark-defaults.conf. When you open it in Notepad, there's a bunch of content that you're seeing here, right? Now in this, you will have to type this one specific line. This one. If it is not there, you add it. I've pinged out in the chat window. Spark-driver.host is equal to localhost, because we're not installing it in a cluster, right? So we will not have it. Please, yes, follow the instructions that I'm giving. It will not be there. How will it be there? What did I say? I said you'll have to copy. Make a copy of this template file. Remove the template and give a name to this way. It will not be there by default. You'll have to copy. Follow the instructions, please. Step 1. Extract. I cannot go at this level. Come on, guys. Extract the zip file that you have downloaded. Step 2. Go to the folder called conf. Copy the template file which says spark-defaults.conf.template. Remove the name template. Open the file. Update the file with this particular entry which says spark.driver.host. Tab separated localhost. You cannot expect me to go at that level. Come on, pick up. Once this is done, you can simply close the file, come out of this folder. This is where now we will have to have the environment variables in Windows set. Now, there are certain softwares which are mandatory. The software that we require is Java JDK. Minimum version is 8. You need to have this. We will verify this. Then you need to have the Python software. You might have already installed via Anaconda. This needs to be there. If it is not there, you need to have this also. It is already pinged. Please look into the chat messages. I have already messaged spark.driver.host tab local host. Please hold on. Otherwise, I'll do one thing. Please hold on. Let me explain the installation. Then I will be sharing you the file, a simple text file, using which you will also be able to follow. Okay, don't try to do it parallelly. You'll not follow me otherwise. Don't do it parallelly. Please hold on. If you try to do it, you'll not follow what I'm saying. You'll be lost somewhere. I'll be there in some other step. I don't want that to happen. Please stop installation. I will walk you through with all these steps and then you do it. Okay, so these are prerequisite softwares. Java JDK. We will have to download this if it is not there, and I will show how to download from Oracle website because Java is now owned by Oracle. Then Python is required, and this Python you might have already installed from Anaconda. If you have not installed, you'll have to install this software. As I mentioned, if you are joining this class, I expect you already know Python class. If you're not familiar with Python, then you just watch it theoretically. In the next sessions, you will be able to do hands-on. Okay, these are minimum two softwares that are mandatory. We have anyways installed Spark. This is something that you have already installed. Now, in order to work with Spark, we also need another software called Hadoop. But we cannot have Hadoop installed just like that. Okay, it again is a separate software, a big data tool software, right? It's a big data tool. So it requires a certain step of certain steps that we need to install. So we'll not be doing this directly, but we will be manipulating this installation for Spark by just bringing one file. This file is called as WinUtils. I will give you the link from where you'll be able to download this. Now, these softwares should be there, and in the environment page, environment variables in Windows, these softwares have to be defined. Let us target Java JDK first. Now, how do I know whether Java is installed or not? Come to your programs, start programs, and then search for Java. When you do this basic search, you'll get configure Java. You open this application. And yeah, you can come to Java here and see view. You will be able to see the version here, platform, the product, right? It has to be minimum version of 8, right? 1.8 basically. That's what it means. When I say update 8, Java JDK 8, it is nothing but 1.8. Minimum is 1.8. If you cannot have 1.7, you can have upper version 1.9, 1.13. Now, if you don't have this Java JDK installed, we will have to install it. Now, how do I get the Java software? It is there available on the Oracle website. So we will go to, again, Google, search for Java JDK 8 download or JDK download. It will give you the Oracle website, oracle.com, Java Technologies download. You click on this, right? You might want to save this link. I mean, write a quick notes. I'm installing Java, and to install it, I'm going for searching the Java JDK software. It redirects us to Oracle website. And if you look at this, this is Java JDK 18 and 17. That is the latest ones. We'll not go with such a latest one. We will basically try to scroll down and we will see here we have JDK 8, JDK 11. Java 8, if I click on that, you will get these options. Click on Windows option, and depending on your operating system's level, you'll be downloading either 32-bit or 64-bit. Typically, it will be 64-bit only. 99.9999% of the systems right now, which run on Windows, have 64-bit operating system only. So this is what you will be downloading. Don't get confused. We are saying Java JDK, then coming to this page, scrolling down, and we are going for Java 8, and then Java JDK version is downloaded for Windows, not for Linux, Mac, Solaris. Come to Windows. If you're working on Windows, I'll work on Windows, right? So take the Windows version. But the point is, you need to have account in this particular website. If you have to download, you need to have an account. So I will click on this and it will ask me for login. When I accept and all that, it will ask me to log in. Single sign-on is required. I have my personal account created very long time back. So I will be using my account to get that file downloaded. I log in and I'll be able to download it. See, download started. If you don't have an account, you create an account. It hardly takes 2 minutes. So I will get my Java JDK and I'll just double click it and install it into my system. Now, once it is installed, you'll also have to see this location. Okay, very important. Come to this and see where the software is getting installed. The location is important. Okay, so we will come here, record this. Right? We'll remember this. It is in C programs, right? C file, C drive program files. This location is important because we will have to set this location in system environment files. So I will go to system environment variables. You can try and type environment, right? As soon as you start typing in Windows, you will get this. Edit the system environment variables. It is available in the control panel. I'll open this option, pop up, and this is what I get. Here, if you see, I have environment variables option. I'll click on that, and this gives me the environment variables details. Now, in this environment variables details, you'll have two sections. One is system variables, and the other one is the user specific variables. In Windows, you can have multiple users also accessing the system, right? So you will be able to either edit here or here. I will be sticking to user variables. We will have to define the environment variables. The environment variable will always be in uppercase like this. Standard names. I will say Java_home. When I click on new, initially it may not be there. So when you say new, you'll get this pop-up. You will type Java_home. This is the name of the variable. For the value, we have checked the path, right? Here we check the path. It is there in C drive program files, and this is the folder. So we will have to give the folder name till JRE1830_301. Right? So we will be selecting that particular location. And once I selected the JDK folder, you can go to that particular location and see that there is a JDK folder. So I'll come here, I'll go to C drive, I'll say program files, and I'm looking at Java. You can see Java, JDK, and JRE. We are interested in development kit, not the entire runtime environment. Only development kit is required. So we will only pass this. The installation is complete with the entire runtime parameters, right? Your entire software, but for your Spark installation, JDK is good enough. So I'm going to define the location here for Java underscore. Along with this, we will also have to have Spark home defined, Python home defined. Okay, I'm not going into the installation of Python now, because as I said, the assumption is that you already have Python knowledge. If you're not familiar with Python, then you will have to hold on till you learn Python to come to this level, to learn Spark. So once you have probably have installed your Anaconda to get the Python, you'll get this Python folder, I mean Anaconda folder. So you're basically going to set Python home to that particular location. Again, you click new and then set that parameter if it is already not there. Then Spark home is something that we are going to define. Now this is my folder, right? In the C drive, in Spark 3, in C drive, in Spark 3 folder, I have this location. Right? So I'm coming from C drive, Spark 3, and then this folder. This is the location that I'm setting here for Spark home. Again, you just double click, you'll be able to see like this. If it is not there, you're going to set it up first. So I'm setting up Java, Spark, Python is already installed, but I'm setting the environment variable. The next thing I need is Hadoop. Right? Because if I have to work with Spark, it requires Hadoop libraries. So in order to get this Hadoop, there's one specific link that we will have to use. Let me talk about that. I'll share this file, don't worry. I will go to this link, which gives us the different versions of Hadoop. We are talking about 3.3.0, which is not there, unfortunately. But whatever is the latest one, we can go there. The latest one is 3.2.2. So I'll go to the latest folder. And if you look at this, there is winutils.exe. This is the file that is required. winutils.exe. You click on that and you'll get download option. You download this file and you are supposed to place this file, winutils file, under the folder which has a name called bin. This name could be anything. This path could be anything. But when you are placing the winutils, it has to be under a folder called bin. So rather than creating a separate path for the entire Hadoop, right, winutils.exe, I'm using this bin folder. For Spark, we already have a bin folder, right? So I'll simply use the same location. Under the bin, I'm placing the winutils file. Just copy paste. After you download the file, place that file here. This location becomes your Hadoop location. Right? I'll remove the bin. This becomes your Hadoop location. So same Spark folder location will be Hadoop. So I'm pointing Hadoop home and Spark home to the same folder. Okay, once these things are done, then comes the most important, the path variable. Okay, so we will have to open the path. Right, double click that path folder variable, and you will see these different options. Now we have installed Java, right? We have installed Spark. We have installed Hadoop thanks to that winutils file. And we also have Python. This path variable should be pointed to the binary files. That is nothing but bin folder. Okay. So whatever the software that we have, within that folder, these folders that we have, right? Within that, you'll have bin folder. So we're pointing to that bin folder. So Java JDK /bin. This is for both Spark and Hadoop. Okay, and this is not required for Python. Bin is not required because all the binaries are there inside this folder itself. So we are adding /bin locations here under the path variable. Again, if you don't have this, you can say new, you'll get new, and then start typing your names and locations. You can browse and then give the options. Once this is done, you save your environment file values. Okay, you save it. Click OK and all that, right? So once this is done, the environment variables are set. Okay, you can see I'm basically talking about those environment variables here. So Hadoop home, Spark home. We're also talking about Java home and Python home. Okay, so once these are done, we are ready to go. Okay, now you might also want to cross-check if it is working or not. When you say Pyspark in the command prompt, right? Let me say command prompt. In this command prompt, you will have to say Pyspark. So we are trying to initiate Spark from Python or Python library. Using Python version and initializing Spark. Spark framework, right? So it's a platform. Inside I'm initializing the Spark platform, and then I'm also calling Python. And you can see Spark context is created. I'm saying because it is a local installation, by default, it will take local star. That means you can do parallel processing based on your hardware. Multiple threads can be used. If this pop-up comes, that means your installation is done. We can also use, right, Pyspark _ Python. Pyspark _ Python option. Set it to Python. If this doesn't work out, you just do this. Pyspark _ Python to Python. And that's all. Well, you'll be able to deal with your Pyspark. All right, so let me share this particular file with you people now. I'll try to share it in the chat here itself. This is data. Yeah. I've shared the file in the chat. You can download it and use it for your practice purpose. You can take time to do the installation steps and all that. Okay, so we will take a quick short break again, and post the break, we will do the actual hands-on. Okay, basic Spark executions. Prerequisite is we need to know Python. Okay. All right. So the time now is 12:12. We will take a short 10 minutes break and come back. In the meantime, if you want to continue the installation, please go ahead and do that. All right, so let's start. The installation steps are very simple. We are trying to have Spark on Windows, right? Spark installation on Windows operating system, that too on a standalone machine. And to do that, we need Java. We need the Spark software itself. We will be requiring Hadoop library, that is WinUtils file. WinUtils. Let me write it again. I'll say WinUtils. .exe. Then we'll also have the Python software which is required, because ultimately we are going to do Pyspark. right? We're writing Python code in Spark environment. So for that, we need Python software also installed. Get these softwares installed, define these in the environment variables in your system. To get the WinUtils, we have a specific libraries, specific GitHub repositories from where we can get the respective WinUtils file. Once the software is installed, we can simply open the command prompt and say Pyspark. When you call this Pyspark, you should be able to see the bunch of messages like this. It should be initiating your Spark by initializing your web UI. This is the standard port number 4040, where you will be able to have the UI. I will be showing that on your local machine. And the Spark context should be also initialized. Your master is local. That means your execution engine is in your local machine. Spark driver will be using your local server or local machine capabilities. This is the URL. Okay, we are basically taking the link like this, and then I will paste it here. You will be able to see the Spark UI only when Spark context is active. If you close your Spark context, then this will not work out. Okay, UI is also gone because everything is memory based, right? So if you release your resources, your Spark context, then all this UI and all those related transactions that we have done using the memory is also released. You'll not have any UI. So let us now go back to this, and we can also try and use Spider or Jupyter Notebook. So let me try and use Jupyter. I can also use Spider otherwise. Either way, okay, I'll use Spider for example. Okay, this is the example .py file. I will be, let's say, open that in Spider. So I will be closing this. You can also run your Spark commands here as well, but I'll not use this. So I will be closing Pyspark from the command prompt here. Now, when I do that, this UI page will also go. For example, let me show you. This is active, right? I can navigate to all these different pages, try and see the content that is available, if it is available in all these pages. But when I say exit, when I'm coming out of this Spark session, now if I do this, look at that. You're not able to access this particular URL because Spark context is not available. Again, in here in Python, I'm doing this in Spider. I'm going to use Pyspark.sql library, and then I'm importing Spark session. Okay, this is like your typical Python execution. From the Python library, you're importing a specific module, Pyspark. Now, using this Pyspark, I'm trying to create an application, and I'm giving a name to it, context versus session. Any name you can give, first example, second example, or Pyspark, and whatever the name you want to give. This is the application name. So we are creating an application name here. I'm calling that as Spark. And I'm initializing the Spark context using the Spark application. Now you have to Be very careful. Python is case sensitive. C is in uppercase. Okay, in Spark session, Spark and S are in uppercase. Okay, so using the Spark session, I am going to call Spark context for this particular application. So when I do that, in the backend, it is calling the resources. Now, if I say SC, you can see it gives us this information. Right, Spark session of SC. This is nothing but this particular application or the session that we have. It's the name that we are giving. And we are using these resources to execute the commands in this particular session or in this particular application. The resources that we are using is all the particular threads that we have in my local computer. Now, how is this actually works, right? So it's very simple. We are doing Python code, as I mentioned. I will create a list here. You can give any name. I'll say L1. Okay, list is a keyword, so I'm not using that. I'm saying L1 is equals to this object. This is a Python list. We can also see that this is the list and it contains 6 values. These are the values. This is a Python object. Now I'm trying to parallelize this object to convert that Python list object into a Spark RDD. So to do that, I will say Spark context and then parallelize this object into RDD. So you have RDD object created, RDD object of Pyspark. Now you'll not be able to view this. When I double click it, you can see I'm not able to view it. Right? It is a memory object. You cannot simply open the file and see. It is an unstructured format. Okay, if I type RDD also, you can see it says parallel collection RDD. Okay, so we are reading at this file from Python RDD. Now we are doing an option called an operation called collect. Collect is basically an action operation. sc.parallelize that we are seeing is a transformation operation. There is no execution actually happening when I say sc.parallelize of L1. That means RDD is not yet created. It's just defined here. Okay, it doesn't have the value. But when I say action RDD.collect, this is where you would actually trigger this operation. Right? You can see the operation is getting triggered and the execution happened. Now we have the data coming into the memory. Okay, this is your print command. Collect is like your print command. We also have another command called glom.collect. This gives me the partitions. Okay, even before that, going to the next line of code, let us go to the UI once again, because now Spark context is up and running. We will have this UI. You'll also be able to get that information here itself when we initiated the Spark context. Right here, you will be able to see that we have the UI generated and all that. By default, the port is 4040. Okay, so the information will be there. So by default, we will get the Spark context using 4040 port number. I will show you how this RDD is generated in the UI. So I'll go to jobs. Right, this is the completed job. Right, this is task. If by default it is taking the sequence number 0. And if I click on that, this is the DAG. If I over my mouse there, it says shows a graph of stages executed for this job. There's only one stage. There are multiple stages, each of which can contain multiple RDD operations. Right? We will basically show it as dot if there is any operation. So here we are doing an operation called parallelize and we are getting the RDD. It's a graphical representation. When we have multiple operations, you'll be able to see the graph also moving. Right? It's like a flow chart. This is the first task which is completed, succeeded. Okay, stages also, you can see the same task, completed stages. Yeah, this is for the stage. So DAG operation, we are doing the parallelization function. This is the first stage, or only one stage is there, and we are collecting the data from Python. Okay, that's all. I mean, you don't need to get into more details to understand what is happening and all that. But this is basically the information that we will have in the backend. Once you get familiarized with all these different terminologies, and when you deep dive into Spark, you'll be able to understand what each of these statements is basically saying here, each of these reports saying. So we'll only look at jobs, whether it is completed or not. Now, when I say glom.collect, it gives us the breakup like this. The output is shown like this. How many partitions are there for this particular object? So I'll have 1, 2, 3, 4, 5, 6, 7, 8. By default, it is creating 8 partitions. Okay, again, this is purely depending on your threads, your system configurations and all that. You can control how many partitions we can create. Remember, there are only 2 things that we can control in RDD. One is the partitions. The other one is how long you might want to keep this object in the memory, persistence. So we are looking at sc.parallelize list of 3. So when I say 3 here, this is the number of partitions that we are able to define. I'll use the same name as RDD. So this is L1, my bad, it's not list. I changed this to L1, right? So I'll have to use L1 here. And the same object now I'm trying to store it in the memory by making only 3 logical partitions. Again, when you say collect, it just gives you the output like this. But when you say glom.collect, it gives you the partitioned data. So it has 1, 2, and 3 partitions. Okay. So this is basically how we will be able to create an RDD. This is the step number 1. This is one way to create RDDs. Did I talk about cluster Yash anytime here when I did the installation in Windows? Did I mention anything about cluster? No, right? Yeah, there you go. That's the answer. So I'm not using a cluster. I'm using a single node. We call this as a pseudo cluster. Okay, and Spark can be installed anywhere. It's not like Hadoop. I'm using the single computer's capability to get the things done. It's a programming interface, right? It's a framework which allows us to do computing. Coming back, one way to create an RDD is from an existing object. This is what we have seen. From a Python list, we converted an RDD. The another one is to directly have a file loaded into Spark memory. So whenever I use SC, Spark context, I'm referring to the Spark's resources. And in Spark context, we have a function called text file. There are many ways to read the data. This is one way. This by default creates an RDD. So when I say sc.text file and give the location, when I'm giving the location, because I'm not having a Hadoop instance, HDFS is not there, right? We will have to explicitly say that this is local file system by adding this file : / keyword. Okay, 3 slashes in fact. When you add this keyword, then Spark will understand that we are dealing with local file system. When you're directly giving the location like this, then it assumes that we are reading the data from HDFS because we don't have Hadoop installed here. We don't have HDFS. But if you're doing it on Hadoop cluster, then this is how we do it. So file : / and then the location of the file, exact location of the file. When I do that, we are trying to dump the data which is there in a physical file into Spark's memory. Okay, this is a transformation operation. Collect is an action operation, and you'll be able to see this. This is the CSV content, cars data set. It is not created as a table. If you observe, you're not creating any table structure here. Okay. So you are just dumping the data as is into the memory. We will be able to also read the data in structured format by using a different function called read.csv. Right? sc.read_csv. Right? There is a very similar function that we have in pandas that gives us the structured output. There are a bunch of operations here, Python commands that we will try and run. And I'll also show how we can read data from a local file system and create a data frame. Okay, we'll also do that. Basic few commands I'll run through. I'll not run through everything. This is a list that I'm creating. X is a list, Python list. From that Python list, we are creating Spark object. sc.parallelize Python list. So X becomes an RDD. Now I'm doing some operation on top of this X. Now, creation of X, this command is transformations. Then I'm doing another manipulation on the X. I'm using map function. This is also a transformation operation. Okay, we're not altering the data at all. We're just doing read-on actions. We want to do some read-on actions, right? So by accessing X, we want to try and map each value of X to this logic. I'm using lambda function. Again, lambda is a special function in Python. When we go to Python sessions, we'll understand. It's called as nameless function. So I'm creating a nameless function, custom function, where I'm referring to each object of X, and then I'm creating Z, Z, right? This logic. This is also a transformation operation. So it actually does not give any result when you say Y. That means actual execution is not happening. Okay. But because you have some operation, it becomes a pipelined RDD, not a basic RDD, but object which is going to be created when you do certain operations. Sequence are right, actions are defined. So hence it's called as pipeline. Now you can do x.collect. Okay, you can directly do x.collect. Print is also not required. You can say x.collect. This is going to only load this object, right? Action operation will be created. You can also directly do y.collect. I'm not doing x.collect. I'm directly doing y.collect. So that means I want to print the output y. But in order to do this printing, I need to first create the object y. And in order to create the object y, I need to load the object x. So this sequence of transformation operations are completed, and then you'll get action operation. Right? So if you have many transformation operations sequentially, we will be doing all of that. And then finally, we will get action operations. When you execute this, all this sequence of workflow commands, will get executed. So let me do that. Y.collect. So it is doing all that right operations, and then it prints this outcome. A comma A, B comma B, C comma C. Right? So we are trying to print it that. Now, if I go to the UI, right, I'll refresh this. Let me just click on that. There are 6 different completed jobs. The recent one is this 5, and this is your stage. So we're first collecting the X object, and then we are doing the Y object. Okay, so this is basically how your operations are completed. We can also go to the previous, any of the previous commands. Let me go to this. This is your text file. Remember, we were accessing the data from text file directly to create an RDB. Right? That is this command. This command. This is the command where we are actually looking at now. This one. Parallelizing and then creating the RDB. We can do similar operations. We can do filter operations also. I'll just execute this entire thing. And we will come here. And you will see that task 7 is also getting created. It's not completed is what it is showing. It should be completed within no time. Same thing. The flow will be similar, but we are doing filter operation. And the output will be X minus 6 should be equal to 1. Whatever the value that is satisfying, we will try to filter that out and then print it. The answer is 6. They're storing that value into Y, right? So whatever the value satisfies this command, we want to save that. So that is nothing but your Y. That is nothing but 6. Okay, so this is how we basically have our basic commands executed. Now, how do we read data from, let's say, the physical location? Yeah, and how do you create a data frame from that? So in order to create a data frame, we need right, the simple logic again. I will be using something called as let's say I'll basically use a CSV file and then try to run the command. Let me just copy that code. Yeah. So the function name here is read.csv. So I'm defining my location, the file name. You can also use the same file name, cars.csv. Let me use the same thing. So okay, I'll just say cars.csv. I'll define this. This is my data. And then I'm trying to use this particular command. This error, don't mind it because I've already done this here. It is going to refer to the Spark from this particular execution. Okay, because I've not have that code here, it is throwing that warning message. That's okay. So here we are trying to get the data frame. You can see I'm using this unit as the name. When I use this command, spark.read.csv, it is creating a data frame. You can say collect option. When you do this collect option, you will get this information like this. Row IDs are all right. We're basically defining the key and value pair like this. Each row information is given like this. Because you used read.csv function. And we're also saying header is equals to true. And we're also saying infer schema. Infer schema true means it will automatically understand what is the schema for each of this value. This is integer, this is float, this is integer, this is float, right? So on and so forth. It will automatically infer the schema also. When you're doing a structured object read, that is when you're trying to get a data frame, rather than connect, we should be using a function called show. Show is a typical function which we use in the structured representation of the data. You can see that it is representing a proper table kind of a representation. Column name is there, and then the values are there. And when you say print schema, it will automatically talk about the data types. This is integer. In Spark, we call the float as double. So I have 2 integers and 3 double columns, that is float columns. Now, if you want to practice more, right, this is just an introductory session for you to kickstart your Spark experimentation. If you want to learn more, then this is what you have to do. Come to the Spark website. You'll have documentation here. The latest release is 3.3. That is what we were using. So I'll come here. Once you come to the documentation, you can see a lot of content here. Okay, you can go through all this content, but under the programming guides, you have the options. If you want to do machine learning, you can go there. If you want to do Pyspark, Python on Spark, this is the documentation. We can try and do the experimentation here. Data frame creation. We can create a data frame using this example, code examples. Right, I did df.show, right? If I pass a specific value, then it will show only one record. Print schema, show. This is what we did. We can also create a data frame by using this command called create data frame. It will convert the data RDD into a data frame. In our example, we did RDD creation separately and directly a data frame creation also. Right? From the RDD, we can do that creation of data frame using this function called create data frame. So all these codes are readily given for you to experimentation or learning. Okay, I'll also go to machine learning. Here you have so much of content. Don't go to this RDD based API because RDD based is already in maintenance mode. It will be deprecated, removed completely. Main guide is what we want to see. Basic statistics, correlations, hypothesis testing, right? So Python codes are given here. How do you calculate correlations? Right? Then data sources. There are some by default inbuilt data sources which you can check. Right? libsvm and image data sources. These are some of the things that we have. Pipeline related commands are there. For data pre-processing steps, we generally use this pipelines. Then if you talk about, let's say, classification and regression, you have, look at that, logistic regression, you have decision trees, you have naive Bayes, survival regression. So many different approaches are already given to us. Packages are already available. Right? And you can also do the code directly from looking at this, or you can go to this folder and get the full example code. Whatever the example that you want to execute, the code example is already there in your system after your installation. In the installations, these Python scripts are given. Right? Let me go to this folder, examples.source. This is the folder you have examples, right? After unzipping, you'll be able to see this examples folder. Here you have source. Under that main, under that you have all these resources. So you can basically go to the resources and see this data sets. Then you can come to Python and then you will have SQL examples. You'll have streaming examples. You have ML related code. The older version MLlib related code is also there. So we are actually looking at ML folder under Python. So logistic regression with elastic net, right? So we can specifically try and look at that particular logistic operation. Let me say, yeah, this is the code that is getting highlighted. And if you open this, it is nothing but your Python script. Python code is it. Logistic regression code. So code is readily available. You just need to understand what is it doing, how is it doing, the capabilities of basics of Spark. If you keep practicing the code which is available here, that is more than the logical side point of right, various things of Spark, the capabilities and all that is what we are trying to understand. So do practice, and then right, future is going to be about Spark, especially when you are doing the production level of executions. You might want to use Spark capability. All right, with this, I will stop here. We will conclude the masterclass for today, and we will again connect in the next session of the masterclass to learn new things. And do not worry if you're not understanding anything here. We will be having the same topic masterclass again next month as well. So month on month, we will be doing it. All right. So we will be talking about that in the repeating this topic in the next sessions. All right. Yeah. See, too many things is not good. Yes. Probably, I'm not sure if you have the experience about all these things. If you have, very good. I would appreciate your right enthusiasm. But if you're not familiar with all these things, then don't experiment too many things at one go. Take one at a time. Again, if you're bringing in Databricks, you'll have JCP, you'll have AWS, you'll have Scala related things, Spark streaming things. So too many things are there. Don't get into all of that. All right. Yeah, the scope of this masterclass is to ensure that people who are learning Python, people who are learning machine learning and data science related stuff, get exposed to Spark environment and Spark codes, right? So that's the objective of this masterclass. And hope you have taken the cue from this particular session. Keep practicing. If you get any doubts with respect to this right, Spark codes, you can always reach out to me. All right. Thank you, everyone, and we'll connect again in the next masterclass. Until then, keep learning, keep enjoying, and stay safe, friends. Thank you, everyone.